Sample problem. Consider a steam power plant operating on a simple ideal Rankine cycle. Steam enters the turbine at 3 MPa and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kilopascal. The mass flow rate of steam through the cycle is 35 kilogram per second. Show the cycle on a TS diagram with respect to saturation lines and determine the pump work in kilojoules per kilogram and megawatts, the heat input in the boiler in kilojoules per kilogram and megawatts, heat output in the condenser in kilojoules per kilogram and megawatt, thermal efficiency in percent, turbine work in kilojoules per kilogram and megawatt, and the power output of the power plant also in megawatt. So for the first question, show the TS diagram. Show the TS diagram with respect to the saturation line. So this one is our TS diagram. So for our simple Rankine cycle, so if you are not yet familiar with the TS diagram, so you can review the presentation in lesson number 1. So this is how our TS diagram looks like. The y-axis refers to the temperature, and then the x coordinate is our entropy. So that's why we have TS diagram. And this one is our saturation curve. So this is how our simple Rankine cycle looks like. So this is a deviation from our Carnot cycle. For our Carnot cycle, our TS diagram would look like this. But since we learned in lesson 1 that this is a very impossible system to obtain, so there must be deviation. First, we cannot create a system. It's not good that what comes out in the turbine is a mixture. That's why we have to extend this one here, making it saturated or vapor, or it has to be a high quality of steam before it enters the condenser. And then after this process of going into the condenser, it has to be saturated liquid. That's why it's here. And then we have to pump it to the pressure of the boiler. So this is our constant pressure line until such time that it will become superheated vapor. And then to close the cycle, that's why we have, this is how our Rankine cycle would look like. I hope that you can familiarize already with how Rankine cycle would look like. So for the TS diagram, so this line here is a constant pressure line. So it means that the pressure here is the same. And based on our problem, that is the pressure in the condenser. As you can see, the condenser is in this side. So it's 75 kPa. So that's why we have 75 kPa in this line. And then the pressure in the turbine. So steam enters the turbine at 3 megapascal. So that's why we have this constant pressure line that is that's 3 megapascal. So as you can see here, we have 2 operating pressures only. We have 75 kilopascal and then 3 megapascal. There's 75 kilopascal on the condenser side and then 3 megapascal on the boiler side. So if you're going to inspect again, so based on the problem, the steam enters the turbine. As you can see, steam enters the turbine at 3 megapascal and 350 degrees Celsius. So that is a superheated vapor. If you forgot that, better review Thermodynamics 1, how to determine the state of steam. So 3 megapascal and 350 degrees Celsius is a superheated vapor. That's why it's here. And then it enters the turbine, and then and the expansion process, it reduces both the pressure and temperature, and then it's given at 75 kPa now in the condenser side. At state 4, that is 75 kilopascal, and then it enters the condenser where it, from a high quality mixture, it became saturated liquid. So for a simple Rankine cycle, one of our assumptions is that it will leave the condenser as saturated liquid. That's why at point 1, this is now saturated liquid. So take note that this one is saturated vapor, and in this side is saturated liquid. So 4 is not a saturated vapor, but it's a mixture with a high quality. So at 1, this is always saturated liquid. And then now, same also with the same pressure, because this one is constant pressure line. This line here is a constant pressure line. This also is a constant pressure line. And then it enters the pump, where from 75 kPa, what pumps does is it increases the pressure of the fluid. So from 75 kPa, it became 3 megapascal. So now it is in the subcooled region before it enters the boiler, and then the cycle continue. So this is our schematic diagram for this problem. Okay, for the first question, we will have to determine the pump work in kilojoules per kilogram as well as in megawatt. So first is we can determine the thermal efficiency of the ideal Rankine cycle by using the formula. Thermal efficiency is just equals to the work net divided by the heat input, which is also equals to 1 minus Q out over Q in, or heat output over heat input. So heat input happens in the boiler because this is where you add fuel in the form of coal. So this is our Q in, and our heat in output happens in the condenser, wherein you are going to release enormous amount of energy to cool the steam. So that's why we have Q in and Q out, and our work net is basically the difference between the output of the turbine and the power input in the pump. So that's why we have work net is work turbine minus work of the pump. So take note also, if you are familiar in thermodynamics 1, that the work of the turbine is a positive work because this is work that does not require electricity, but because of the expansion of the turbine, because of the steam. And then the pump is a negative work because it requires electricity. So we have those components. So in order for us to determine these variables or these quantities, we will have to find the enthalpies. As you can see, we have 4 points, state 1, state 2, state 3, and state 4. So we have to find the enthalpy. So take note that if we are dealing with steam, we will use the steam table in finding the enthalpy. If we are dealing with air, you can use the ideal gas equation or the air table. If you're dealing with refrigerant, then you will have to use the refrigerant table, which you are also able to encounter in thermodynamics 1. So finding the enthalpies first, we will start with at state 1. So at state 1, as you can see here, just like what I said a while ago, this is a saturated liquid because this one is a saturated liquid. This curve here is the saturated liquid curve. That's why this is a saturated liquid at state 1. So to find the enthalpy when it is saturated liquid, all you have to do is just to find the steam table. Our Enthalpy at state 1, it's just HF at, or the enthalpy of the liquid at 75 kilopascal. 75 kilopascal because this one is the pressure here is the same, and that is 75 kPa. So look at your steam table, go to the saturated liquid table at pressure, and then look for HF. So HF at 75 kPa in your steam table is 384.39 kilojoules per kilogram. And then, in order for us to solve for whatever process is in state 2, let us compute also the entropy at state 1. So the entropy is also the same, that is the entropy of the fluid, of the liquid rather, at 75 kPa, and that is 1.213 kilojoules per kilogram Kelvin. And then we will also need to compute, to get in the steam table, our specific volume, the specific volume at 75 kPa, and that is 0.001037 m³ per kilogram. So these are the properties that we will need at state 1 based on the saturated liquid 75 kPa. Next is at state 2. State 2, as you can see here, this is now, state 2 now is in a subcooled liquid. Because it is in this side here, so that is a subcooled liquid. So for this process, we can see that since this is a PS diagram, so a vertical line here means that the entropy is the same. Same also with this one here. So we can see that S1 is just equals to S2 because this is a vertical line. So if that is the case, then our entropy at state 2 is just equals to the entropy that we got in 1, and that is 1.13. They are just the same. So we will need that for us to compute the variable that we will need later on. Another formula that we can use here is the pump work, since we all know that process 1 to 2 is a pumping work. So process 1 to 2, you have to raise the pressure from 75 to 3 megapascal. So the pumping work is just equals to this one. So the specific volume to 1 multiplied by the pressure difference. So that's V1 times delta P. So if that is the case, then we can compute the pump work using this variable, this values that we already have. So V1 is 0.001037 m³ per kilogram multiplied by pressure at 2. Just make sure that the pressure should be in kilopascal. That's why we have to convert megapascal to kilopascal. So that's 3000 kilopascal minus 75 kPa. That's the pressure at 1. So our pumping work is 3.0341 kilojoules per kilogram. As you can see here, we already have our first unknown, and that is the pumping work. The pumping work is 3.0341 kilojoules per kilogram. So we also have to compute it in megawatts. So we will have to multiply this one with the mass flow rate. So the mass flow rate based on our given is 35 kilogram per second. So just multiply our pumping work by 35 kilogram per second, then we will have pumping work equals to 106.2 kilowatt, and then divided by 1000 for us to obtain the megawatt equivalent. That's 0.1062 megawatt For letter A, our answer should be 3.0341 kilojoules per kilogram and 0.1062 megawatt. So this means that this simple Rankine cycle or this steam power plant needs 0.1062 megawatt of electricity to operate this pump here. So that is the answer for letter A. Also, we can calculate pumping work using the enthalpies. It's just that we do not have the value of H2 yet. What we are going to do is we are going to reverse the process. We are going to use the pumping work to obtain H2. That is why, so pumping work is equals to H2 minus H1, that is 84.39. That's why we have enthalpy at point 2 is 387.4241 kilojoules per kilogram. So as you can see here, there is an increase of enthalpy from 384.39 to 387.4241, even though it is a subcooled liquid. So this is the value that we will need also for the computation of the heat input in the boiler, because as you can see here, we'll need 0.2 and 0.3. So we are good with at state 1 and at state 2. So let's go to state 3. As you can see here, state 3, after leaving the boiler, for a simple Rankine cycle, it has to be superheated vapor. So that's why we have, you can also verify this using your steam table. You just have to check the saturation temperature at 3 megapascal. So if the saturation temperature is less than 350, then it is a superheated vapor. So for this case, this is obviously a superheated vapor at 0.3. After leaving the boiler, this is a superheated vapor. So we will use this idea to compute the enthalpy at 0.3. So we will use our steam table. So instead of using the saturated liquid, you will use the vapor table in our steam table. So to get the enthalpy at state 3, that is H at 3 megapascal and 350 degrees Celsius. So if you're not using the steam table by Canon, but you're using the steam table in our book, then you will have to interpolate. But you can also use online steam table. Just make sure that it is a superheated vapor calculator. So our enthalpy at 3 megapascal and 350 degrees Celsius is 3,115.3 kilojoules per kilogram. So as you can see, you can also find out that the enthalpy at 0.3 is the greatest among the different states. And that is, for this case, 3,115.3 kilojoules per kilogram. Now we will have to get also the entropy at 0.3 so that we can use that idea to get the entropy at 0.4. So the entropy at 0.3 is entropy at 3 megapascal and 350 degrees Celsius, also using the superheated vapor table. So that is 6.7428 kilojoules per kilogram Kelvin. And then for state 4, so at state 4, upon leaving the turbine, so now our steam enters the turbine and it produces work by the expansion of the steam, and basically it reduces the pressure from 3 megapascal back to 75 kilopascal. But now we do not know the quality of the steam. So the quality refers to the amount of vapor there is per total, so in the total mass. So in this case, we do not know where this point is. That's why we will use what the data that we already have. We cannot assume that at state 4 it is saturated vapor, but for this one in the condenser, this is one of the assumption in simple Rankine cycle that it will leave as saturated liquid, but not saturated vapor upon entering. So we'll use our mixture formula. So if we have mixture or saturated mixture, we will use this formula. So HF4 plus X4 HFG4. So basically our HF is the saturated liquid enthalpy at this point. X is the quality. HFG is the difference between HF and HG, or the enthalpy of the liquid and the enthalpy of the vapor. This is just the difference. So if we say HFG, that is just HF or HG minus HF. So there are steam table that contains HFG. So if your steam table does not contain it, all you have to do is just to subtract HF from HG to obtain HFG. But we do not have yet the value of these values here. That's why we will use the steam table. So we will have to use steam table in solving the quality X4. Now we know that this is a mixture, so basically our entropy can also be calculated at 0.4. The entropy can also be calculated using the same formula, but now in terms of entropy S. Since this is a constant entropy process here, S3 is equals to S4, that's why we can use the data that we already have here, that S4, this S4 here, is equals to S3, that is 6.7428. And then for SF4, that is saturated. That's why we will use SF at 75 kPa. So in this case, we will use the saturated table. So at pressure of 75 kPa. So SF4 is SF at 75 kPa. So that's 1.213 kilojoules per kilogram Kelvin. And also for SFG4, that is SFG at 75 kPa in your steam table. That's 6.2434. So if you already have S4, SF4, SFG4, then you can get quality X4. So by substituting the values, our quality is just 0.8857. As you can see, if it is equals to 1, if X is equals to 1, then this is a saturated vapor. If X is equals to 0, that is a saturated liquid. For this case, since this is 0.887, it is somewhere here in the almost at the saturated vapor side. So this is a steam with high quality entering the condenser. Okay, so since we already have our X4, now we can get the value for H so that we can substitute that one in this equation. So our HF4, we can still get that at a saturated liquid table, HF at 75 kPa. Let's rate 4.39, which is equals to H1, right? Because H1 is HF, that's why it's the same. HFG4 is the HFB at 75 kPa. That's 2278.6 kilojoules per kilogram. HFG is basically the latent heat of vaporization or condensation, which can also be found in your steam table. Then our H4 is just equals to HF4 plus X4 times HFP4. So our enthalpy at state 4 is 2402.546. Obviously, it has to be lesser than the enthalpy at H3 because there is an expansion that happened in the turbine. So we have 2402.546 kilojoules per kilogram. So now, we already obtained all the enthalpies. So the summary of enthalpy values from our calculation both in the table and in our mathematical computation, we have H1, H2, H3, and H4. So these are the enthalpies that we will need in computing the other unknown. The first one, which is the heat input in the boiler. As you can see here, if you look at the boiler is between process 2 and 3. So basically, by energy balance, the heat input is just equals to the change of enthalpy here in the boiler. Because we will assume that there is no work, it is obviously implied that there is no work input in the boiler, but only heat input. That's why our Qn is equal to the change in enthalpy. So Qn is H3 minus H2 in the boiler, or the heat input. This is also the same line here. So H3 minus H2. This is the boiler side, right? So that's why we have H3 minus H2. So by substitution from our summary of enthalpy, we have this one. And then our heat input in the boiler in kilojoules per kilogram is 2,727.8759 kilojoules per kilogram. So we also have to get the megawatt equivalent of this heat input. That's why we will have to multiply it by the mass flow rate of the steam. Why is it that we're using 35 kilogram per second all throughout? Because this is just a one loop cycle, meaning whatever flows in the boiler is the same steam that flows in the turbine, in the condenser, in the pump. That's why it's constant, 35 kilogram per second. But in the next discussion, it will be different because there are modification already in the cycle. It's not as simple as this one. That's why by multiplying it by the mass flow rate of 35 kilogram per second, we can cancel out kilogram. The result is kilojoules per second, and that is kilowatt. So our power input now, so this is now power. That's 95,000 plus kilowatt, or that is 95.5 megawatt. So this is our answer for the heat input in the boiler in kilojoules per kilogram and in megawatt. So this is the amount of heat that you are going to input in the boiler. So this is from coal or from the fuel that you will use in the combustion in the boiler. Next one is the heat output in the condenser. Unlike the heat input, the heat output is the waste heat, because this heat will not be used anymore, but it will be exhausted into the environment in the form of a chimney or in the cooling coolant that we are going to use. So this is the heat output. So our objective is in the design of steam power plant is to minimize this one and increase this work in the turbine, because basically this is what gives us electricity in homes, in power plants, in industries. So the heat output in the condenser, if you're going to look at our schematic diagram, it's just the difference in the enthalpy at 0.1 and 0.4. So our Q out is H4 minus H1. So substituting the values, our heat output in the condenser is 2018 joules per kilogram. And then if we multiply it by our mass flow rate of steam, our power output is 70.64 megawatt. So as you can see, this is a large amount of heat that is wasted in the process. As you can see here, we have 95.48 megawatt of energy from coal, and 70.64 megawatt is wasted. That's a large amount of heat. That's why there are actually a lot of modification that we can do to improve a simple Rankine cycle, so that we can still reuse this heat. So now that we already have Q output and Q input from our formula for thermal efficiency, which is 1 minus Q out over Q in, we can get the fourth unknown, which is the thermal efficiency. So that is 0.2602 or 26.02%. You can see this is a very small thermal efficiency, meaning our power plant is 26.02% efficient, meaning 74% of heat from coal or from our fuel is wasted and only 26.02% is used for the generation of electricity in a generator. So our objective is always to increase the thermal efficiency. So if you become engineer, you will have to take note that you have to increase thermal efficiency by decreasing the Q output and increasing the Q input, or maintaining the Q input but decreasing the Q output. So the next unknown is our turbine work. As you can see in our illustration, our turbine is basically between 0.3 and 4. So this is the turbine. This is between 3 and 4. Same also here. And our pump is between 2 and 1. So from that, we can get the turbine work as the change of enthalpy between 0.3 and 4, that H3 minus H4. It is output because this is a work that is expected that we can produce from the expansion of that turbine. Note that connected in the turbine is our generator, right? So our generator is the one that generates electricity, and will go to the transformer and distribution hubs, going to our residences and homes, and that's in the scope of electrical engineering naman. That's why we will not deal with that one so much. For the turbine output, that's H3 minus H4. So from our enthalpies, so we can get turbine output as 712.745 kilojoules per kilogram. Again, multiplying it by 35 kilogram per second, our power output is 24.95 megawatt. So this is the output only of the turbine, and this is not yet the net power output. But this is just the output of the turbine. That's 24.95 megawatt. So basically, our power output from the power plant is what we are looking for, the capacity of the power plant. So the net output of the power plant is the difference between input minus output. So from our solution calculation, our input is 95, our output is 70.64. That's why the power output of the power plant is 24.84 megawatt. This is the net work, or the capacity of this power plant. That's almost 25 megawatt. Or we can also use an alternative formula, which is the difference between the turbine output and the power pump input. So you can see whatever you produce in the turbine, you will get a fraction of that power to run the pump, right? So the pump cannot run on its own. Unlike the turbine, you have to plug one to electrical source. That's why we have to subtract it. So the net of the power plant can also be computed as the work of the turbine output minus the input in the pump to run the pump. And that is 24.95 minus, from our question A, that's 0.1062 megawatt. So our net output can also be computed using this alternative formula. That's why we have 24.84 megawatts, which is just the same. As you can see here, we can get the power plant output using this formula or this formula. So the output of the power output of this power plant is 24.84 megawatts. So the summary of our answers. So the pump work is 3.0341 kilojoules per kilogram. Then we also have heat input in the boiler, heat output in the condenser, thermal efficiency, turbine work, and then the power output of the power plant, which is 24.84 megawatt. Take note that this 24.84 megawatt, there's still generational loss in the generator and then distribution loss in the transformer. That's why we cannot expect this to be 24.84 megawatt when it arrived into our homes or into the consumer. So basically for this plant that we analyze in this problem, we will expect to produce almost 25 megawatt of electricity. So how is it compared to the actual power plant? So we have here power plants, for example, in a biomass power plant in Negros Occidental, which produces 25 megawatt. So that's almost the same to our problem. So this is a 25 megawatt biomass power plant in Negros Occidental. You may also be familiar with the Bataan nuclear power plant, which can produce 621 megawatt of electricity. However, this one is not yet operational because of some safety legislation or some issues. We also have the largest power plant in the Philippines, which is the coal-fired Sual power station in Pangasinan. That is 1,200 megawatts. So this is an enormous amount of power compared to what we calculated. This is in Pangasinan. And the last one is the Three Gorges hydroelectric power plant, which is the largest power plant in the entire world, which can produce 22,500 megawatt of electricity. So that's an enormous one naman. I hope that you enjoyed this discussion. If you have questions, just reach out using our chat box.